It's my pleasure to introduce Paul Kocher, who is coming from to us from that other part of the state, Northern California. And I have to, of course, on behalf of the pseudo-random number generator that's called Southern California weather, I apologize for this horrific weather outside. We generally do a better job. Anyway, like I said, it's a pleasure to welcome Paul. He has been in the area, working in the area of security and cryptography for quite some time. I'd estimate at least 15 years or so, right? Maybe
20.
20.
Started early.
He looks younger than, yeah, for quite some time. I guess ever since he escaped Stanford?
Yeah, even before. I'll sort of talk in some.
Right, and he's had a number of successful commercial ventures to his name, but also a number of research contributions. Among the commercial ventures were a company called ValueCert. Some of you may have seen it or heard of it. That was in the early 2000s, and currently he is involved with Cryptography.com, which he also bootstrapped and led to an acquisition by Rambus. And he's currently the chief scientist and CEO of that division, Rambus, right? Cryptography.com. He's best known probably for the co-authorship of SSL 3.0, right? The standards. Also for the side channel, the pioneering work on a side channel analysis, cryptanalysis, and a few other things, including work on satellite TV and Blu-ray and that kind of thing, like DRM, I would say, related activities. So, without further ado, the floor is yours.
Thank you. Can everybody hear me all right? I can't tell if the mic's on or not. So, no reaction means you probably can't hear anything I'm saying. Okay. So I'm a failed veterinarian. I was going to be a vet, went to Stanford, was excited about working with animals, and this thing called the internet came along, and when I ran out of money for tuition, I started doing computer projects because I like computers and had played around with how you take video games apart when I was at home as a kid, and suddenly this was useful for breaking things, and at some point came across ciphers, and they just, yes?
Can you turn it on?
It is on or not on?
It's not on.
Is that better?
Yeah.
Okay. And this idea that you could have a fully defined math problem, a plain text and a ciphertext, that you could even know both of them, and some little key that would determine how to turn, say, the ciphertext back into the plain text for more messages. I couldn't easily solve this for this key. Just bugged me. It was like this idea of a math problem that was designed to be hard to solve as opposed to the ones you get in classes that were easy to solve. Got me really kind of interested in the area of cryptography. So read the papers I could. I'm self-taught. I don't think I've ever taken a class in cryptography. So basically I'm grossly unqualified to be speaking to probably most of you here. So I started doing crypto projects, broke a lot of things, asked questions people weren't asking, which led to some fun research results. And also, when I graduated school, instead of going off to vet school with my biology degree, I started doing consulting projects full-time. And that bootstrapped the company, and I put most of my focus on cryptography research. But along the way, I've worked in a bunch of different projects of some successes, some failures, some that, depending on how you look at it, they're a success or a failure, and lots of things that never got off the ground that I didn't even put here, because you only want to show people things that at least went somewhere. So protocols like SSL3 is probably an interesting case study in how much we learned about protocols, and also when somebody has proven something secure, that seems to be a harbinger of more cryptanalytic results against it. So I can talk more about this later if you're interested. Gene mentioned side channel attacks. So one of the things that I was hired to do was to look at the security of devices, and didn't have nice reverse engineering equipment. I had a cheap oscilloscope from Fry's Electronics and the ability to measure time using a PC. So using the tools I had, I found stuff that would let me break things. That led to some interesting research papers, but also some very practical implications I will talk about in more detail in this talk. Built some hardware to break DES, done various companies. I've also been an advisor to a bunch of different startups. And in my company today, we do lots of things. We build hardware cores that are tamper-resistant and secure in different ways. We work on systems that are designed to recover after attacks. So there's a system as part of Blu-ray that we designed that lets you put code on the disk, and the code can query the environment and even run code in the processor to try to detect what attacks might be present. We we just launched yesterday a new system that's part, again, a Hollywood distribution system for 4K movies got launched that we did the security for. And I know people sometimes aren't that excited about DRM, but it's actually one of the areas where there are attackers who are really breaking stuff, and companies will spend money on security. So it's a place where the battles are happening. And if you're a good ER doc, you go to where people are getting shot. If you're a cryptographer and you want to go deal with the real world of stuff, you go to where things are falling down. That's one of the places where it's a slugfest going on. So it's an interesting place to work. Also, one sort of thing, if you're interested in if you start working in cryptography, I would also suggest for you to look at ways that if you're successful to go back and support the field. So there's just a fund for students that we created with some of the money from my company's acquisition that's being managed by the IACR. And if you're studying cryptography, hopefully that will benefit some of you. So to start the talk here in terms of the sort of meat of it, if we go back in history, back to the 1940s, 1950s, or even before that, the problem in cryptography was getting enough computation. When you're trying to do a device like here's a code wheel from the 1500s, you just can't do that many computing steps using mechanical things that you turn. Or you look at the World War II era cipher machines, and you have pieces of metal and plastic and gears and Bakelite, and everything you want to do in terms of computation requires a cog and a spring. And there's this very impressive elegance to the mechanical engineering, but the computation power you have ultimately limits the strength of your algorithms. And if you look at the failure of the Enigma machine, for example, this was really a failure to have enough computation on the encryption side, and then that enabled cryptanalysis to be possible. If you look forward, sort of fast forward to today, we have a situation where the algorithm designers have won the game. So if you look at the modern algorithms like AES or triple DES, they're effectively unbreakable, assuming that what we think is correct actually is, against people who just throw compute power breaking keys. And the margin of victory is increasing over time, and we expect that this will be an ongoing trend. So if you look, for example, at going if you add a little more compute power when you encrypt, you dramatically increase the compute power to break something. So say I go from single DES to triple DES, or I'm going from a 56-bit key to really a 112-bit effective key. So I've tripled the encryption effort, and I've got a 2 to the 56-fold increase in the effort required for an attack. So this sounds pretty good, but there's something just hideously wrong when you step back and look at reality. So we've got strength in the algorithms, but the outcomes that we're actually seeing in the field when it comes to computer security are bad and getting worse and worse and worse. So the number of breaches and the severity of the breaches this year is worse than last year. Last year was worse than the year before. Essentially, the belief among all large corporate networks right now is that they are significantly infiltrated, and the question is just how severe is it, and what is the adversary trying to do? If they're just trying to steal the information, that's less disruptive than somebody who's actively trying to be harmful. So most of the smart attacks, so if you can keep out at least the people who are going to break your computers and only let the ones in who are at least smart enough to be rational, I mean, you're doing better than Sony is, and you feel you're successful. So it's a very depressing situation on the street if you look at computer security right now. Another way to look at this is, if you look at the just measures of the number of threats and the severity, they're all going up exponentially. To contrast with an industry that's done a pretty good job, if you look at aviation, for example, you have logarithmic improvements in the safety of aviation. So if you look back in the 1940s, with the amount that each of us has flown, some of us would have died in airplane crashes if we'd flown that much in the 1940s. But right now, most people don't know anybody who's died in an airplane crash. Yet, knowing people who have flown 10 million miles, I mean, lots of people have flown 10 million miles, or a small group of people collectively have. So we have, on one hand, exponential improvements in safety. Our industry has not even got things to level off yet. So why is this? So there are basically three trends that are driving both the economic success of the computing industry, but also the problems that we struggle with on a daily basis on the security side. So we have more and more devices that are shipping, that are doing all kinds of useful stuff, many of them connected. We have more valuable data on those devices, and each device's complexity is also growing exponentially still. So what does this mean from a security perspective? It means we have more targets, more reward for attackers, and more vulnerabilities for the attackers to exploit. And this sort of triple set of exponential curves, even one of them will be really hard to deal with. But the effect of these is effectively multiplicative. So the situation on the ground is really going to keep getting worse. And the reason for this is actually fairly straightforward. If you take a system and I double the number of critical elements in it, and you can measure that as lines of code or transistors or just some number of the critical elements, modules. If I double that, the probability that there's going to be a catastrophic bug in one of them is, if it's linear with the number of elements, it means that I have then squared my probability of having 0 fatal bugs. So if my probability of surviving was 20% before, and I square that, I'm maybe down to 4%. Now, in reality, the security problems tend to go up reflecting interactions, and especially the way that C and unsafe languages work, where one pointer error in a big complicated system brings the whole thing down. The real risk actually tends to go up more as the number of interactions, and so you get something even worse than what you would assume with linear growth in risk. And this assumes, of course, that the flaw densities aren't increasing. But if you take the same size engineering team and you force them to produce twice as much code, they're going to actually have worse bug densities for having to deal with so much more. Just like if you had to write a 5,000-page paper instead of a 5-page paper, you're going to have more typos per page than if you for the long paper than the short one. So if you look at other areas in engineering that have dealt with failure, there's been a lot of learning that hasn't applied very well to the computer security space. So in the case of structural engineering, for example, here's the Silver Bridge built in 1924, and being a security discussion, obviously the bridge collapsed. The reason was that there was this notion of fracture critical components, where if you can build a bridge which basically has single points of failure. And computer security systems have this question of, there's single points of failure. If this thing fails, the whole thing collapses down just like this bridge. In structural engineering, the idea, modern bridges aren't built with single points of failure anymore because they fail. Some truck may hit that particular piece. There may be a bad weld. There may be something we don't know. So you try to build your bridges in ways where it requires several different pieces to fail for the security to hold together. So if we look at should apply this thinking to, say, a typical Internet of Things device, your internet-connected refrigerator that sits in your home network. It can talk to the other devices in your home network. It talks to the outside. What do we have? So we have bits of DRAM. Well, if I can flip a bit of DRAM, I can usually break your security using that. It may require some creativity on the attack side, but usually that will destroy the security. If I can flip a bit in the flash, I can change a bit of code. Something bad is going to happen. All the logic gates in the CPU, all these different things end up being really every single thing you look at in a modern chip has a very high probability, like substantial probability of being a security critical piece. So in a typical device, I estimate there's somewhere around 10 billion individual elements that have to work perfectly for the security to hold together. And in 10 years, this may actually increase to about 1 trillion. And the likelihood of, even if each one has a very high probability individually of being good across the whole system, then you're still very likely to have a failure. So let me talk about emergent properties for a second. So if I go and I study individual neurons, I really don't understand brains. And if I go and I study ants in isolation, I'm not going to understand colonies. If I go to understand TCP/IP, I really don't get Facebook from that very well. There are things that emerge as you put lots of these things together. And one of the things that we get as humans, though, is we look at the individual piece that we understand, and we think that we're going to understand the properties of the overall system. With security, our intuition that we get from understanding individual lines of code and individual functions will give us this confidence that we understand the security properties of the systems that are built from them. But it turns out that insecurity is this emergent property which reflects complicated issues across large code bases and people and interactions and user interfaces and manufacturing supply chains and all of these kinds of things that when you think you understand that code you're writing, you really don't. And I'll talk a little more about the way that the things that you learn in computer science school actually trick your brain to thinking that you know what's going on, when really you're just deluding yourself into thinking that you've got a secure system when you don't really. And so the underlying issue here in many ways is that we're taught to think about functionality. Like if you're assigned to go produce a system that will sort a big pile of data and output the sorted data. I mean, if your code works correctly for the data that you feed into it, you're going to create the functionality and it's working correctly in the normal situations. This is mostly what you're going to think about when you're building a system. It's what are you trying to make it do, and does it do that? And if it can do something else, like if it's useful in some unexpected way, it has some extra capabilities, that's actually probably a bonus. I'll give an example in a second here. Reliability is a little trickier. Like if I'm trying to make a system that's always going to work properly, well, now I've got to deal with Murphy's Law. I mean, there's going to be weird data inputs that are going to come around occasionally that might cause my sorting routine to do something that it shouldn't. So I'm making my reliability harder because that nature might throw at me something that is out of the ordinary. Now with security, we have to deal with every possible maliciously chosen situation. And so here, if there's something that it does that isn't intended, this is the problem. So take a buffer overflow. If I've got a system where my login screen is a buffer overflow, well, okay, it might actually be useful. If I forget my password, I can get in. Helpful. But over here, it's exactly the problem. So the negative, the thing that your system isn't supposed to do that it does, is what is your security or your insecurity. But that's not usually what you're thinking about when you're doing engineering. So the strategies and the thinking around security are fundamentally different. And in terms of the places that things fail, in terms of what we're looking for when we're hiring people, the thought processes on the architecture team, the idea that you go think about trying to make it do stuff and that yields a good security outcome is the wrong thought pattern. It's the thing where you walk into a place and you look at the question that people aren't asking, not what is the thing intended to do. And in many ways, the very capabilities that have enabled computer science to be so successful are working against us here. And I'll talk about layers of abstraction and use that as a sort of a side theme as I talk about side channel attacks. So when we want to cope with complexity in computer science, we hide it with layers of abstraction so that you don't have to be thinking about the transistors when you're trying to figure out what color your web page should be. And your brain would just go crazy if you didn't have this ability to abstract your languages and your ways of thinking and accomplish complicated things with very simple expressions that get implemented with a big layer of software and hardware underneath. But these layers of abstraction, the purpose of them is to conceal the underlying details. So it's great for complex engineering, but what it means from security is that the layers are hiding risk. And when you think about what's going on when you write something in JavaScript, you're not thinking about what's happening at the transistor level. But if there's some transistor property that's important to you, you're going to be so far disconnected from it that you're going to have a very hard time achieving some security properties that might matter to you. And the example that I'm going to talk about here that related to this is the one of how do you keep a key in a device? So there are lots of useful reasons that you'd like to have a device, for example, that can get some inputs, produce some outputs using a key, and you want to keep the key inside. So maybe I'm building, or maybe the outputs stay in the device, but like I want to decrypt the network packet. There's a key that will secure that decryption process. Some input comes in from over the network. I'm going to produce a decrypted output. And I don't want the attacker to get my key. And keys, cryptographic keys correspond to your identity, to your authenticity, to all of the things that we want to do in computer security, where you'd like to be able to differentiate good guys from bad guys. It normally boils down to the good guys hopefully knowing a key that the bad guys don't. And if you're a bad guy, you want to get the key. Because if you get the key, you can masquerade as the good guy, steal their data, etc. So the algorithm problem here has been solved for many years. AES, RSA, ECDSA, whatever your sort of off-the-shelf crypto standard, at least ought to be able to do a good job of protecting this from a mathematical perspective. But the algorithms are built with the unwritten assumption that the attackers only get to see the inputs and the outputs, and nothing else, and the correct inputs and the correct outputs. Now, when somebody takes this algorithm written as basically a list of mathematical steps and goes and translates that into hardware software, you can go and build a correct implementation that works correctly in normal circumstances. But the way that they fail is very important to the attacker as well as the defender, and isn't really part of the written set of assumptions here. So I'm going to use glitching first as an example, which is something that we do in our lab all the time when we want to try to pull keys out of a device. So the question here to ask yourself is, what happens if you're doing a calculation involving a secret and you make a mistake? Your device doesn't faithfully produce the right output. Now, if you're thinking just intuitively, you might think, oh, okay, it's just going to produce some junk that somebody will throw away and the protocol will fail and have to do it over again. And it turns out that intuition completely misses the point, which is really that if you make a mistake when you're doing your crypto, you almost always end up breaking the warranty on the crypto, and usually it's exploitable. So if I can cause your processor to make an error really anywhere in what it's doing, I'll figure out a way to turn that into something that I can leverage to mount a successful attack. There's a great paper from 1997 by Dan Bonet and some others at Stanford giving one example of this, but there are lots of other sort of ways to do it in effect. And there are all kinds of things that can cause a glitch that have to do with in-the-weeds but absolutely critical engineering details. Like, what can somebody do to your power line coming in? If your power voltage sags during the calculation, even briefly, you're going to end up not being able to have your transistors drive strongly enough. You're going to have some interesting, hard-to-predict effects in the chip. At the end of the day, your chip's going to make an error. If the reset line has a little bit of a glitch on it, that eventually, you make that glitch start with a very, very tiny glitch and make it bigger and bigger. Eventually, a couple of flip-flops are going to be the most sensitive. So I can reset maybe a few flops and something interesting will happen. That compromised the Xbox. There was an attack involving glitches in the reset line. So this isn't theory, this is practical stuff. What happens when you exhaust the EEPROM? So I burn your memory, your EEPROM, many, many, many times using an untrusted thing, and then it will not hold the bits faithfully anymore. And then some critical code gets, I put some critical code there later, some bits will change. And I can often find a way to exploit that. So lots of things can make these kinds of mistakes, and they're just fatal from a security perspective. So there's some research questions here. So there are things that we're doing today with making our crypto algorithms check each other, but there's no really great general theory about how do you ensure computation correctness and make it so that you get an input, how do you get an output, and know that it's correct in an efficient way that you can actually build in a chip and ship it to a customer to let them protect their stuff. So this is an example of an area where I think that there's a big gap between the needs in the field and what research you can deliver. Another example is, if you just go back to your first electrical engineering class, all of you, I think, know what a transistor is. It's a switch, and depending on the voltage applied to the gate, that determines whether or not electrons can flow across the substrate there. When electrons flow, they come from somewhere. They come from the power supply. And if a transistor has got electrons flowing from it, that will result in ultimately more electrons coming in from the source. The moving electrons also produce RF radiation that you can also measure from the outside. So one of the questions I asked myself when I started looking at crypto devices was, hey, what do I see in the power consumption? So I went down to Fry's Electronics, bought the cheapest oscilloscope they had. This was the year after I graduated from college. And went into a dark room. All I had was the phosphor on it. It was too cheap to buy one of the ones that had any digital stuff in them. And looked at the power consumption of smart cards as they were running, and I saw something that looked a lot like this. And I knew it was an RSA operation. I knew what the Chinese remainder theorem was. I knew that there were two pieces to the sort of heavy lifting of the operation, computing a result mod P, a result mod Q. And you can see that. And in a darkened room, I could see this characteristic trace showing that at least I could see something coming out of the crypto. Now that's really interesting. And as somebody who kind of thinks, okay, you go to all this work to find 2 to the minus 80 biases in your crypto routines, and suddenly I'm seeing stuff on a screen just using a cheap oscilloscope from Fry's. And also, here's an EM trace from an RSA device also. You're just seeing the crypto, not breaking anything yet. But this was immediately really interesting. And it turns out you just zoom in on the oscilloscope, run the operation a few more times, and you'd see something that would look like this. And this is still something that you see from devices. This is from a modern 4G smartphone. We stuck a little coil of wire next to it, ran that to fairly simple circuits to sort of tune and clean things up a bit, showed an oscilloscope. And this is actually what we saw off the device. This is pretty typical. Now inside the RSA operation, the operation basically goes to, for each bit of the key, it will always do a squaring operation. And if the bit's the 1, in the loop, it will do a multiply as well. And we will run through this, taking our secret bits. 1 bit at a time, it's getting mixed in. If the attacker can figure out the bits of the key are 0 or 1, they break the security, obviously. Well, so I look at this. Okay, there's a square. This is a square and a multiply. Well, square and multiply, that's a 1. So I see 2 together. That's a 1. It's a 0, 1. I'm just reading the key off. And this is something where still there are hundreds of millions and billions of devices shipping where you go and you take $300 worth of, stuff here connected to an oscilloscope and a PC, and just looking at this within seconds, you can see the key. But it doesn't even end with that. So the next thing is, it's actually a much more subtle issue going on, which is that the effect of what's going on is got all kinds of correlations as well. So if I think about say an AES operation where I'm going to do a calculation very quickly in hardware, the effect of every single transistor has some statistical effect or statistical correlation to the overall measurement I'm taking across this huge busy chip with all kinds of things going on. Now it's small. Now it might be less than a millionth of the total, or even a billionth, but there's some effect. So if I have a transistor that, let's assume its operation is uncorrelated to everything else going on in the chip, and I take a measurement. And I do that many times. I'll see some kind of a distribution, usually kind of it looks like a normal distribution, because it's the sum of lots of different kinds of things going on. So at some point in the computation, I ran millions of crypto operations with different inputs, and I plotted the measurements at this point in time, and I see a normal distribution. But now let's just assume for a second I know the key. If I go in and I say, okay, given that I know the key for a second, if I go to the middle of the 7th round of AES, and I pick bit 12 of some intermediate, and I just take all of my measurements here and divide them into 2 subsets. One for which I had a 0 there, and one for which I had a 1 there. That one arbitrary intermediate calculation. And then, don't think I'm going to do my one-on-one right now, sorry. I plot my distributions. It turns out that they're very slightly different. I've exaggerated that here just so you can kind of see what it looks like. But these distributions have different means, or they may have different shapes to the tails. And what this means is, pardon the pun, means here. What this means, though, is that my partitioning of all my measurements into 2 different subsets, if the subsets have different distributions, was correlated to something that really went on inside that device. Whereas if my partitioning was random, I just tossed coins that had nothing to do with what really happened, these subsets would have identical distributions, ignoring sampling error for a second. So if I see that I get a difference here, I have found a correlation to what really went on inside my device. So I can break keys out of all kinds of things with this. I run the device with a bunch of inputs, collect power traces, I make a hypothesis about, for example, a piece of my key, and compute a couple steps in based on the hypothesis, look and see whether the result of whether these subsets have any differences from each other. So I average the ones for which I have a subset of 1, average the ones for which I have a 0, look at the difference of the averages, multiply the y-axis, and if I see some spikes here, then I know that I found something correlated to what's going on inside. And you can break any crypto algorithm you want with this, because if there's no effective countermeasures in place. So this is just, again, involved asking the question, okay, what are these transistors doing to us? And if I go back to these layers of abstraction, we had here a case where just the effect of 1 or 2 transistors in a single logic gate in a giant SoC with all kinds of crazy stuff going on in it. I can pull it out. This is way smaller than even my sampling accuracy of my A to D, because I've got all this noise that I've got to filter out anyway. It's just another source of noise. Well, that caused some properties at the logic level, which affected the CPU, which gave me visibility to the software, which broke the crypto, which broke the protocol, and ultimately broke the business objectives. And there have been payment systems that had to be reworked because keys could be exposed to this. It remains a big problem for various people who are trying to protect keys if their devices aren't protected. This didn't get caught for a very long time. And part of, because even though this was work 15, 20 years ago, people were paying attention to just their layers. There were people who were working on the algorithms, people who were paying attention to the software, and people who were paying attention to the transistors. But there really weren't people who were paying attention to what the implications across those were. And today in the crypto area, there's a lot more attention to this issue, but there's still, from a security perspective, there's a lot of attention and specialization in layers and subfields, but people tend to get comfortable there and tend to not look at what the implications are in the areas that they're uncomfortable with. And when you start asking questions, well, like, what are the cryptographic implications of what goes on in the USB stack? Well, the USB stack in most devices runs at very high privilege, boots up very early on, because you might need it for various power on things, and is written by poorly paid engineers who have got a crappy job of writing USB stacks. And so they have bugs in their code. So there are big implications there, but not very many crypto people want to go look at USB software. So I mean, you just have a lot of these places where the big issues over here, my comfort zones over here, and trying to make sure that you're going over and exploring some of these other areas that are unfamiliar is a way to find lots of interesting things that are being missed. And then the other way to look at this, when I identified this problem, I also sat down and think, what's the opportunity here? And filed a bunch of patents on all the ways we could think of protecting devices. And that led to a part of my business today, which is licensing those patents. And we license about 9 or 10 billion chips a year, including many, many billions of smart cards and TPMs and government things and big chips and phones and everything else. Because if you want to protect your keys, we patented the idea of protecting yourself against this attack. And so you pretty much need countermeasures unless you're willing to let your keys be revealed to somebody who has got a couple $100 worth of gear from Fry's Electronics. So if you find something interesting, there's always that question of what can you do with it? Now, going from a patent to a licensing business involves lots of scars and lots of work and so forth. It's not I'm giving you the summary that misses all the hard work in between. But again, if you have something interesting like this, entrepreneurship in the security space is a really exciting area right now. There's huge demand already for solutions that actually give you some tangible benefit. And lots of demand for snake oil doesn't do any good at all. But it's a great space in terms of the need for innovation and the willingness for people to buy products that are innovative. So I'm going to talk a little bit here about the strategies that I'm taking in terms of building products to try to tackle some of the security problems that are out there. So putting on a little bit of a commercial hat, but I'm not trying to sell anything, from a kind of question of why take certain approaches, what do I think are not what won't work and what will. So if we step back and look at this problem and the complexity issues that I talked about earlier, there's some things that I think are going to be fundamental to navigating as a technology industry from where we are today to at least a somewhat better space or a less bad space or a space where the problems grow less exponentially than they otherwise would. And one is that I think the problems have to be fixed below the software layer. I think we built our foundations wrong, and if you build a building on loose sand and it keeps collapsing, well, you can keep blaming the guys that are building the building, but at the end of the day, you need to have a better foundation. And right now, the hardware approach to security is one of saying, this hardware could conceivably give you security if all of the software running on it was perfect, and if my hardware doesn't have any bugs in it. Well, those ifs are wrong. There is no complicated software stack today that is bug-free. And in fact, there's no big processor today that is bug-free. I can state that probabilistically because I don't exactly know what the bug is, but if anybody wants to take the bet here about whether there will be another Windows security bug in the next 6 months, you pick your odds and I'm on for that bet. And likewise, if you want to bet as to whether Intel's latest processor is going to have a security bug somewhere in all of its microcode, or even the latest ARM cores or the MMUs in your pick your large mobile chipset, there will be bugs. They're just too complicated, and these devices have been built for speed, not safety. So we have to do something different in the hardware. That's one thing I believe. The second is that whatever we do has to be deployable as an additive element. And this just reflects the economics and reality, where if you require somebody to re-architect the things that they've already got, you're instantly going to get overwhelmed by the complexities of the supply chains, the difference between who has liability and who has control. Like, if you want to go and fix Intel's processor security, and Intel does a pretty good job. I'm not picking on them because they're worse. I'm picking on them because actually they do a better job than just about anybody else. Well, you can't go do that unless you go work for Intel. And even if you do work for Intel, well, you can't slow the processor down. You've got all these teams working on different things. But you can add stuff, because Moore's law is giving us transistors cheaper and cheaper. So the idea that you could do something that adds a few pennies, it doesn't affect the old stuff, but might do something useful with some additive element, is much, much more tolerable. And it's also much more practical to deploy, because you can go build your additive thing as a separate team, and you don't have to go deeply embed yourself into a whole bunch of other teams that are working on complicated stuff. And then the third part is that whatever you do has to address two critical parts. What is in the device itself, and what is the infrastructure and context around it? Because when you want to go and produce 1 million or 1 billion of something, the supply chains and the manufacturing processes and the efficiencies and optimizations and the procedures and all of this stuff has been done already. If you have to reinvent any of these wheels, like even if you have to just shift from a merchant foundry like TSMC over to the IBM trusted foundry or whoever owns it now, you're going to increase your costs by orders of magnitude, and you're going to be dealing with old technology instead of the latest technology. And for a big SoC project, you just can't do that. So you have to figure out how to work with all of these legacy things and do so in a way that addresses these supply chain and production processes. So going back to this case of the keys in a device, the architect might start with saying, I just want each device to have a unique key, maybe generated from some master key, and this will be programmed in the factory and stored in the chip. Very easy to describe what you'd like to achieve there, but the number of things that fall from that is huge and complicated today. And so how is this going to be distributed? Where is it going to be stored in the device? How is it protected? How is it audited? What happens in each of the factories? What if the factory is malicious, and so forth? So there's a whole bunch of sort of next level down questions that need tackling. And I've been putting a lot of energy to figure out how to tackle these kinds of things. So the approach architecturally that I am the most excited about involves putting extra blocks of hardware into big chips. And so if you look at where we are with software security, it's just not going to get there. I've talked about this sort of on and off through this talk here, but if I look today, if I've got a really high value secret in a chip that's protected with software, the attacker might need as many as 3 bugs in order to steal that. So a browser bug, for example, to compromise the user account on the device, then an OS bug to become root in the OS. And if I've really got trusted execution environment like TrustZone or something like that running in my ARM processor or Ring 0 on an x86 processor, somewhere it's maybe a little more protected, I need one more bug here to get through that, and I've got the secret. And each of these surface areas, the app, the OS, and this environment here, are all sufficiently large that the probability of there being vulnerabilities is overwhelmingly high. So it's just a question then of, okay, I have to go to enough work to find these 3 bugs, or maybe I can find one bug that lets me through all 3. Like, if I can figure out a way to make the processor make an error, then, well, that just gives me 1, 2, 3 straight in a row there. And there's, for example, just a really cute paper recently on an attack where if you, called Rowhammer, where you bang the DRAM in sort of worst case scenarios, and the probability that innocent memory accesses would cause an error are small, but it turns out that if you bang the DRAM in the right ways, you can make mistakes, and those mistakes become exploitable, of course. So things like that may be able to give you something out here, like your JavaScript that's been turned into native code using JIT, letting you flip bits down here. And there's not really any help in fixing the bugs in software, because bugs are being made faster than they're being fixed. And so, kind of in my career, I started working on algorithms, and then focused on protocols, thinking, well, okay, I've got to get better pieces with those, and the software guys kept mucking it all up. Kind of gave up on software. Hardware is nice because there's at least no level underneath you where you get abstracted and somebody ruins your security as a result. So we can put it, but instead if we put a separate hardware block here with its own perimeter, and it's small enough that we aren't way up this complexity ladder or curve, we can build something where a team focused on security can make this block, and we can have some hope that it's built for security rather than breakneck speed. It's your, it's your armored vehicle rather than your race car. And I'm optimistic still about this strategy. And over time, we can have many of these. So if you kind of think how you store things that explode, you spread them around. Like here's a ordnance depot. It's hard to see, but there are lots of little huts, each holding little bits of explosives. If one goes off, it's okay. I mean, that part, the little hut is lost, but not the whole thing. This is a Serbian ammunition storage facility before it exploded. You know, if you look at the approach that people have been taking to a lot of these security systems, it's piling more and more complexity into one giant perimeter, sticking more and more missiles in the room, hoping none of them explodes, but when one does, the whole entire system comes crashing down. But here you can have, you know, a separate perimeter for payments, and one for VPN and one for memory protection. That'll cost you more transistors, just like this costs you a little more land, it costs you more roofing materials and more electrical wiring. But those things are cheap enough now that it's worth spending a little bit of what Moore's law is giving us to get some security instead of packing more and more giant cores in. I mean, I think most people would rather have a smartphone that was secure than a smartphone that went from having 12 processor cores to 16 processor cores. So we're building cores to do this. So we're building hardware blocks that drop in. They'll manage a one-time programmable memory, someplace you can store device unique secrets. They'll talk to an untrusted interface, so all the commands that come in are digitally signed and encrypted, so the keys can be delivered in a way it's secured with previous keys and so forth. You can do public key handshakes with machines in the cloud or with machines in factories. And then we deliver out, the outputs are pretty simple. There's things that you know are authentic and authorized to set, like whether you're in debug mode or not, and things that are also authentic plus secret, so a key. Yeah?
Does this, since it does all the public key handshakes, does it also handle revocation?
Question, does it handle revocation? Well, so yes and no. So sometimes you handle revocation in the back end. So if you're talking to a device, if you can authenticate what keys it has, you just revoke in the back end. There also are ways you can blow bits here to move life cycles along and revoke capabilities that were present previously. You also, in this, can add capabilities ephemerally. So for example, if you want to turn debug mode on, you might only want to turn that on for a single power on. So there, an RNG value gets generated in here. The authorization is bound to that RNG and has other limitations so that it just naturally expires. Obviously, in a device that's offline, getting fresh revocation data is a problem. So that question of what freshness you have to talk to somebody trustworthy to give you revocation status ends up being kind of a protocol and application specific issue. But generally, the tools are here to build that. But there's an external piece that needs to go with it for a full revocation system to be.
So does it speak, can it be made to speak certain revocation protocol?
Yes, within some limits of, I mean, if it's possible to do it in a block like this, you can probably make it work. But there are fundamental limitations of what's present. So like in a block like this, I don't really know what time it is unless I go talk to somebody that I trust. And so time is a very subtle issue in a chip for which you don't have a consistent clock available.
And lack of a secure clock makes it very difficult to talk in a timely manner or something.
Right, so do I know if it's fresh revocation data?
Right.
But if I can talk live to somebody, I can generate a random value, I can get a proof saying, okay, for this random thing you generated, here is the latest revocation status. So if you figure out what's possible, then the question is, can the implementation do it? And if it can't, then it's just a matter of engineering, to get it done. So if you take another example, if you look at the way debug modes work in most chips today, there is a global password. If it's comes in through the test interface, there's some matching, maybe a few bits that get XORed together to determine whether you're in debug mode or not, if it's going to be persistent. Very hard for the chip designers, very hard. It's not secure. You break one chip, you break them all. But you start making something which is done with crypto. It's much easier for the design team because they just drop a thing in. The policy gets set through signatures. And it's also a lot more secure. So there are a lot of these sort of foundational things like debug modes and PLL configurations and stuff like that that have been long neglected by the security people, but are fundamentally need to be cleaned up in order to be able to build a building that's robust on top of these foundations. So I'm low on time. I'm not going to spend time on this, but there's just tons of stuff that goes in factories, boxes that manage keys, boxes that talk to the boxes in factories, tamper-resistant hardware that goes in them. It's about 70 people in my company who just do this kinds of engineering to build this stuff. And it's just a lot of kind of unglamorous work, but again, it's a critical set of foundations that haven't really got any attention before. And what I'm hoping is we build these foundations that we can then start building more and better things on top of those over time. And this question of scaling, once you've got a foundation where I can get a key into a device and trust it, well then I can do useful things with that key. But all I can do is put a key in a device, and it's going to be stolen the first time somebody finds a couple of bugs in the software. I can never build that foundation, build that building that I want on top. So what happens? I'm going to go back to sort of my last couple slides here. I'm going to look at this question of scaling again. So we have Moore's law with the number of transistors, whether it's the total transistors or transistors per diode, however you want to measure that. Exponential growth curve has been continuing there. It may slow down, may hit the wall at some point, but it's been going for a long time. But the value you get is actually, especially per transistor, is diminishing because you implement the high value thing first. Like if I take Microsoft Word and I double the number of lines of code in it, it's not twice as useful because it does all the things I want a word processor to do for the most part. And there's a prioritization of the features that you put in. So the high value features get implemented first, and the lower and lower value things get added later. But the risk is growing with the complexity. So if we end up with the net benefit, or the value we're getting here, is the benefit of the feature minus the risk that it added. And if we don't deal with security, the value of systems as they get more complicated falls. It's less useful to have a dangerous system that has just some slightly more useful capability in it. So if we can't control the risk, the more complicated products are less valuable than the ones that we had before. And the most extreme example of this is after some of the Snowden leaks, both Russia and India went and ordered a bunch of typewriters for high sensitivity information because they were kind of the only things that they could have some confidence weren't bugged. Now you can actually bug typewriters too, so I'm not sure this was actually the right decision to make. But the idea that the typewriter is more useful than the laptop computer really strikes home that if you can't deal with this risk, the technology industry is going to be stuck. Another way to look at this is 1995 Mercedes, pretty nice car, $15,000, worth quite a bit of money. Windows 95, you really wouldn't want to run that today on the internet. But if your Mercedes from 1995 had Windows 95 in it, what would the implications of that be today when you're trying to drive that car around? So if we look ahead, may you live in interesting times is sort of the famous curse. The future in security space is going to be very exciting. Now, if you are a patient at a hospital, you don't want an exciting hospital stay. But if you're a doctor, it can be pretty interesting to see the patients that are exciting and interesting and challenging coming through. But the problems are going to get worse for at least the next 3 to 5 years. There is no technology on the horizon that will be able to even keep pace with these trends that I've been talking about. And there are things that will help, but if I can get rid of half my bugs, but the number of bugs quadruples, my technology that got rid of half the bugs is useful, but I haven't actually fixed anything. In fact, I've still lost ground. So but that doesn't mean it's all hopeless. In fact, we look at the macro level, the trends are bad. But in individual systems, they can be made very robust. There are specific outcomes where smart people work on specific systems and they hold up very, very well. But the question ultimately is, can we contain these risks? Can we get adoption of the technologies that we do come up with? Because it's easy to write an academic paper that doesn't turn into a product. It's also easy to make a product that doesn't reflect the academic research, but the two have to work together properly. But the question of this ultimately will determine whether or not society can keep getting new benefits from technology. And it's certain that security will consume an ever-growing portion of our engineering resources in the same way that, for example, environmental compliance consumes an ever-increasing percentage of our attention in manufacturing. The things that heavy industry could do a long time ago that were incredibly damaging to the environment are unacceptable today and don't work at the scale that we have for our modern society. In the same way that the things that maybe worked for Windows 95 from a security perspective don't work today. The things we're doing today are not going to work properly in the future. So the need for people who are smart in security and can help tackle these problems is going to be absolutely acute and will ultimately determine whether or not the technology industry succeeds at continuing to scale and whether society gets the benefits of what technology can provide. So that's the end of my prepared part of the presentation. If any of you have to run off to class, you're welcome to do that, but I will stick around for questions.
So this is a kind of big question. I know a group of people who are trying to implement smartphone voting, like voting for the president or the whatever state. And I thought it sounds like a great idea, but now you kind of convinced me that it's not really possible yet. What's your opinion? Is it possible within the next 3 to 5 years to have a smartphone voting app that we can trust and trust our democracy to?
Well, so if one of my employees gets voted president, you probably have a suspicion that something went wrong.
Right.
And so no, I mean, the visibility into knowing whether, and vote, the security model around elections is enormously complicated because you have lots and lots of fraud that occurs, lots of effort to hide the fraud. You don't want centralized failure modes. You want to have it where fraud requires a bad person in every single precinct going around and moving paper ballots around in ways that are observable. You need to have it, and the other thing is that democracy fundamentally depends on the loser and their supporters believing that the outcome was fair. And if you have an opaque system where you really can't give the loser and their supporter confidence that it was a fair election, or at least close enough to a fair election that it was within some noise, the democracy is at risk. And there were enough problems with the debold electronic voting systems a number of years ago that, at least for elections in democratic societies, I don't think we're there yet. I don't know that we'll ever be there. There's nothing that wrong with using paper for some things. In fact, if you have something you want to write down that you don't want somebody to steal, paper's the right place to do that still. Paper and pens work pretty well. My passwords are on a piece of paper in my wallet and encrypted in a way that hopefully most non-cryptographers won't break also. But that piece of paper, you're not going to electronically steal it out of my wallet. So no, I don't think smartphone voting for democratic elections is appropriate. For things like shareholder votes and small, unimportant elections where the future of society doesn't depend on it, maybe. Yes?
So all these chips, you flashed the slide where you have chips planting in different parts of manufacturing process. Like, is this supposed to be some part of some grand architecture? I was confused by the slide. You said, "Oh, we don't have much time to do that."
This slide?
Yes, where you have different people in my company are doing these unglamorous things of making these, I understand, manufacturing processes more secure, or giving these manufacturing lines ability to create keys on devices that are being produced. Are these special purpose engineered solutions for a particular product line, or is it part of some grand scheme where you try to create some standards for all these type of essentially all electronic manufacturing engineering? I mean, this is how I read this slide.
Yeah, so the question is how widely deployed will things get? And standards can only go so far. You need to have products that you can deploy. My company works with most of the big chip makers, so we have publicly announced relationships with like Qualcomm around our crypto manager technology I'm talking about here. We've also announced relationships with Broadcom and ST and a whole bunch of other chip companies. So there are only a smallish number of companies that can afford to build state-of-the-art foundries and the wafer processing facilities and so forth. So the hope is to get the foundational pieces deployed in all the places that matter, and then also have security blocks on as many of the chips as possible in order to enable things like authentication and key management. So it's an evolutionary process, though. I could describe my requirements before how to get something in there. I can't go from where I am today to a complete solution in one step because the number of touch points is too large. But if I can provide enough value to the chip maker that they'll improve their security processes and get some things that solve their needs, and then work with their customers to help address more of their needs. Over time, different people can use this in different ways. I'm hopeful and optimistic that there is a longer-term path toward having secure enclaves and environments and devices where you can do useful things, maybe not as fast for video game playing as you would have for your main app processor, but places where you can have $1 million worth of value in a device that is in somebody's hand in the field and not expect that the person who has the device will actually be able to steal your $1 million keyword data. And that would be kind of the point where, and DRM is an example of this. I'd like to have at least the source encoding for my movie sold to lots of people who would like to pay $10 to see it, but I spent $400 million making this movie. Can we get to the point where at least the bits before they've been sent to the display can't be stolen, or at least won't be stolen within some economically reasonable attack. And I think we will get there eventually. The question is how long and how widespread will the deployments be. And all of this stuff has to be done first. And the stuff that was in effect before we started working on this was largely, duct tape and baling wire. Somebody took a PC and wrote a little bit of code in some, a little C program that would program things in the assembly line, and somebody, put the do not touch sticker in red in the factory, and it's just sitting there. To give you some idea of the factories, like some of the gear we work on, they asked questions about how heavy it was, because they were people would steal it, and because you've got low-wage people, and so the threat environments around these locations are very complicated. But getting, again, the problems are all solvable, and this is what my company has been building to try to tackle these. And what I'm interested in ultimately is finding ways to get from where we are to somewhere where there is a path toward better and better things. Yeah.
So switching context a little bit, DRM.
Yeah.
So in the research community, I have a feeling that there's a kind of a dichotomy. Some part of the community thinks DRM is a wonderful research topic that's just full of fruitful things to do, and the other thing is things like the shingles, it's just a nightmare, just popping up and bothering people, and annoying everybody. And so I wonder if you had any opinion on that, and especially on the futility or non-futility of software-only DRM.
Okay, so the questions around DRM are one where, so I have a philosophy that's different from, say, Richard Stallman's view. I mean, my view is that a computing device is more useful to me if other people can trust it. I don't necessarily have to trust me. So my bank might not trust me to always make the right decision, but if they can make my device more useful if they can have certain understanding of its properties. In the same way that a movie that I can watch on my device is something I would like to be able to consume, and the transaction I can do with a movie studio if I can give them certain confidence in the attributes of my device. So there's a philosophical question, and you can debate that. When you dig one level down, then the question is one of how can we do this in ways that mean that my data is protected so I control it, but the movie's data is protected, the studio's data is protected in a way that they control, and the two are properly separated, so it's not limiting what I can do with my device. In fact, it's enabling me to do more things. Architecturally, DRM is driving more security innovations and deployments than a lot of the sort of quote-unquote pure security objectives, like protecting user privacy. So if you kind of want to go into the streets where the victims are, the bodies are, DRM is a place where there are real attackers, real stuff going on, real technical problems, and ultimately things that people will deploy if you come up with innovations there. So the things that we're building may have a DRM use, but they also can be used for privacy, and they're not limited to that. But DRM often will be the use case that drives the decision to put the chip area in. Other times the decisions to give us die area may be even driven by other things that have nothing to do with really security, like how do you take your chip and sell it in a locked configuration so that you don't have to have as many different configurations of your chip. You have to manage your inventory process. I mean, just stuff like that security can help with. And people stealing stuff in shipment or out the back of your factory costs you money. Maybe it's not, again, the purest ideal problem you want to solve at the end of the day. But if we can't build a technology that works for a DRM system, we can't build a technology that's going to work for protecting any other kind of data that we've got. So you can follow wherever you want in the philosophy, but the engineering problems are really, really interesting.
Well, let's thank the speaker again.